So if the collision model states that this is what has to happen in order for a reaction to occur, then we have to also introduce the idea that at the moment that these molecules collide with each other, that certain things must be true. One of those things is what we call some kind of intermediate molecule. A very temporary, not going to stick around for long, intermediate, where both things kind of connect together in a certain way, and then after that intermediate has been formed, almost immediately it's gone. Okay? Now, when it comes to collisions as well, think three-dimensional problems. If they do not collide in exactly the correct way, in other words, if their orientations are not pointed in the right directions, then the reaction cannot occur the way it's predicted. So here we see just kind of like a very basic example. We see one molecule coming in to interact with another one. In this particular case, one part of the molecule interacts with another, they collide, and then the collision actually results in the breaking apart and forming of two new molecules, right? In the second one, since that collision does not happen in the exact right way or orientation, we see that the overall collision does not result in a reaction. So think about the likelihood that bigger and bigger molecules will collide the exact correct way. It becomes less and less likely to happen the larger and larger you get. Smaller molecules tend not to have as much problem, but that's why we use mostly smaller molecules when we talk about chemistry. This is a whole nother beast if we're talking organic molecules, macromolecules, proteins, enzymes in the body. For our sakes, we deal in what we would call small molecules in chemistry. Beyond small molecules, things get much more complicated. And a lot of what happens is we introduce the theory of how charges work, and orientations based on charge are more important in bigger molecules. But for simplicity's sake, there are a couple of things we're going over in the collision model that have to happen. The next is going to be that of an activation energy. So when it comes down to it, not every time that a reaction is starting is it going to actually get all the way to the product stage. Think every single molecule interacting with each other in a beaker, they all have to have at least a certain amount of energy in order for that collision to result in new molecules being made or being formed. That amount of energy required is the activation energy. And you'll see various different analogies for it. One of them that I think is most common is the golfer trying to get the golf ball over the hill. Hit it with just enough power, it's going to go right up to the top and go right over to the other side. Hit it with not enough power, it won't go up and over the hill. It'll just come right back down at you. That activation energy barrier is the one that we're going to talk about when we get into what we call reaction mechanisms, which is what's next. In order for the reaction to occur, it must have the minimum activation energy. And what we're going to do is we're going to introduce this idea that we can manipulate whether or not a reaction will occur and how fast it will occur by manipulating the activation energy itself. And we'll talk about several ways that we can do that. For now, let's look at our first reaction coordinate diagram, where we look at how much energy is required to get something to happen. Okay, so the potential energy contained within your molecules, the energy required to get over and get your molecules to interact with each other, rearrange, versus reaction progress. So this is not time. Okay, down here on the x-axis, do not confuse reaction progress with time. All reactions take differing amounts of time, so if we put time down here, these diagrams would all look wildly different. To make things easier on ourselves, we use what we call reaction progress. So from the quote-unquote beginning of the reaction with our reactants to the end of the reaction with our products, this is what amount of energy is required in order to get this to happen. Draw the diagram in your notes. It's like, so this is the thing that we're going to talk about next. So up here is what we call the intermediate, okay? Those 3 dots indicate like this is where it's going to collide. So it's not a bond. It's just kind of the pathway of the collision for this particular type of intermediate. Please do notice that these two are different. Couple of pieces of information we're going to get from these diagrams. The first is the activation energy, which we always draw from the reactant's beginning potential energy to the top of that hill of energy that we have to get over, and the overall reactions energy. So change in E, total energy, is going to be between the reactants and products. So a lot of information that we're going to get off of these reaction mechanism diagrams, or these reaction coordinate diagrams, if you will. Yes, ma'am?
So, like, where the molecule bends and, like, where the bond forms, is it always happening there? Like how it says
This?
Yeah, like, will it always happen there? Or?
This is just kind of giving you an idea of, like, what's happening over the course of this reaction.
Okay.
Yeah. It's a good question. It's not necessarily, like, this is what will happen at this point, and this is what will happen at this point, and this. That is more of a, over the course of a reaction, it's not just this stuff breaks apart and then all of a sudden it's this stuff. There's a lot more going on, right? Up until now, we've just kind of assumed bonds break, bonds form. We're moving towards the what's in between. Okay, and that diagram is still there. The little complex that is present at the activation energy point is referred to as a transition state. Sometimes it's called an intermediate. Sometimes it's called an activated complex. There's a couple of different names for it. I use intermediate and transition state kind of interchangeably. This activation energy is sometimes referred to as a barrier. For us, we'll just call it E sub A. And you need to recognize that when you see E sub A, it means activation energy. Say again?
Which one means activation?
EA.
Oh, okay. Thank you.
Moving on. All right, so Maxwell-Boltzmann distributions is kind of this intermediate topic here. I believe we've seen the term before. We've even discussed what Maxwell-Boltzmann distributions are. For our purposes in this chapter specifically, we're going to discuss Maxwell-Boltzmann distributions in a very general way. We're just going to say that the impact of temperature is what changes how many molecules have higher kinetic energy or lower kinetic energy. So these are the distributions we talked about when we kind of introduced how temperature impacts the movement of molecules. At higher temperatures, more molecules have higher amounts of kinetic energy. But do remember that if I could peer into a beaker and I could point my radar gun to clock how fast each individual molecule was moving, that they would all have different speeds. Even if we used a thermometer to read that the temperature of the beaker was, say, 90 degrees Celsius, right? We would see that everything has its own individual speed. It's just kind of how it works. Nobody's ever moving all at the same pace. Same thing with human beings, right? If you're talking about synchronized swimming, some of them are pretty good about synchronizing, some of them aren't so much, okay? Same thing kind of happens here when we talk about our molecules. Some of them are going to move really fast. Some of them are going to move really slow. We use our thermometers as an average measure of temperature, which is also an average measure of kinetic energy, okay? Really what we're getting at is at any temperature, molecules have all different kinetic energies, okay? When we increase temperature, we see more molecules get more kinetic energy, and we kind of see that fewer molecules have that smaller amount. That's the big takeaway from Maxwell Boltzmann. And again, we've talked about this in the past. You've seen this graph before. I believe it was like chapter 5 when we did thermodynamics. So this is not necessarily a new concept, but I do want to remind you that this is another factor that makes our reaction kinetics difficult, right? So this is just another thing that impacts whether or not that collision will happen and the reaction can proceed. What we're getting to is that how that effect on temperature actually comes into play in a reaction rate. So we said at the very beginning of this chapter that one of the major factors that affects the rate of a reaction is the temperature of the molecules that are being reacted together, right? And we kind of said, well, it makes sense because all the molecules speed up, right? And since the molecules are moving faster, the reaction should move faster. In reality, what we're seeing is as we increase temperature, the rate of collisions increases. Even if the collisions are not the right ones, like we saw in that first diagram, even if the collisions are not correct, we're still seeing a higher number of collisions overall. So more collisions means more likely that things are going to collide correctly and that the reaction will happen quickly, right? Because everything just moves faster. We said that. What we want to take that description from, everything moves faster. That's why temperature affects rate. We want to take it from there. We want to say everything moves faster, which means more collisions in the correct orientation occur, and the reaction proceeds faster because of that increased number of collisions. Okay? Our descriptions get more and more complicated as we move through.
So, like, the more the merrier?
Yeah. The more collisions there are, the more likely you are to hit the target. Put it that way. The more times you shoot at the target, the more likely you are to hit the center. Can I move forward? You do have access to this PowerPoint, don't you?
Yeah.
From last week? Okay. What we're going to use, the only math in this section on temperature and the effect of temperature, is this one right here, where the fraction of molecules can be found through taking the activation energy and dividing it by the gas constant R, that's what that capital R still is, times the Kelvin temperature. So this is one of our equations in this particular section. There aren't a ton in this section. This is probably the least math intense between the middle and the end of this chapter, yes.
I was just wondering what the numbers were for R.
Capital R?
Yeah.
0.08206. I'll put it on board. You remember from our gases chapter But there were a lot. But in this one, we're going to use that one. Okay. From that particular fraction of molecules, we get the Arrhenius equation, where we can relate K, which is the rate constant, to the Arrhenius constant, which is capital A. So do not get capital A confused with E sub A. Capital A is a constant, the Arrhenius constant. E to the activation energy divided by RT. So that is the Arrhenius equation for a specific chemical reaction that relates the rate of a specific reaction to its activation energy and temperature at which the reaction is taking place. Yes.
Would the R be the same?
R is the same as this one, yep. R is going to be the gas constant.
Does the frequency factor stay the same for each problem?
It's a given, though. Just like any other thing we've done in the past, that would be one you'd have to be given. With this equation, I'll tell you the most common thing you'll be asked to solve for. Is either K or EA. Now, when we did our integrated rate laws, we learned how to go from the natural log of something using E, right? How do we go the other way? How do we get that E to become something else? We would have to take the natural log of it. So the same process, but in reverse. And we'll see that here in a little bit. Okay, that brings us to the Arrhenius equation on a graph form. If you take the natural log of both sides, you can rearrange this and you can fit it into a graph. This chapter is so heavy in graphs, I know. But it's because the data fits really well when we can make it fit a straight line. And you guys have seen for yourselves how useful graphing something can be, getting an equation, and using that equation to solve for predicted concentrations. Right? So in one of those exercises I had you do today and yesterday, those practice problems, I had you solve for a concentration at a time point that was not given to you. That is very useful, especially if you can get that for something you're predicting to be formed instead of something that you are using up. Because then you can calculate, well, how much of this will it create? Once I know how much it creates, then I can kind of put myself on a time scale. But if I know it's going to take 2 days to produce 5 molar of something, then I can set it and I can walk away. It's pretty awesome. It's really useful. You guys can hopefully see the usefulness of some of these things. If you can predict the concentration of something way in the future, or how long it's going to take to produce a specific concentration, then you can actually better prepare yourselves in like a lab setting, which is the whole idea behind chemistry. Okay. For this particular exercise, you would graph the natural log of your rate constant. So this would be several different reactions that were measured at different time points. And then you would graph it versus 1 over T. The usefulness here is in calculating what EA is, right? If you know that the slope is EA, your activation energy, over the rate constant, you can calculate what EA is, right? If I tell you that some number is this, can you calculate this? Of course you can. I'm not going to have you graph this. I would give you a graph, tell you the slope, and say, what's the activation energy? That's like your example you can look forward to. Okay. Not looking forward to reaction mechanism. All right. So reaction mechanism is our next beast in this chapter. And it's pretty much the last hard thing in chapter 14. Reaction mechanisms are ways of representing an overall set of reactions. So we move away from a one equation reaction into those reactions we've talked about in the past where there are maybe 1 or 2 or 3 steps to get to the overall reaction. And we try to determine what we call a reaction mechanism so that we can predict a reaction rate, or a rate law, if you will. These can happen through several steps, like we said. So far, we've dealt with only one-step reactions, right? We've dealt with A plus B makes C. This is a one-step. If we now say that what we really want to get is an overall process to make a different thing altogether, we can do it in multiple steps. And you've seen the multi-step approach before, right? Kind of, sort of. You remember our Hess's law problems. Okay. When it comes down to it, each individual step can be referred to as an elementary process. It's just kind of terminology. Don't focus too much on that. What I do want us to focus on is the fact that when we add things together, so when we look at different reactions, we can refer to them in a molecularity form. Okay, and hopefully you can kind of see the pattern if you just study this table for a little bit. We can call something unimolecular, we can call it bimolecular, we call it termolecular. Uni means one, bi means 2, ter means 3. What we're referring to when we say those things are our reactants. So 3 reactants, termolecular. 2 reactants, bimolecular. 1 reactant, unimolecular. If we look at individual steps, I can say, what is the molecularity of steps 1 and 2 of this reaction? What would you reply? Bimolecular. There's 2 and 2. So both steps are bimolecular. What is the molecularity of the final reaction? Termolecular. Okay? So just kind of simple terminology from this particular section. All right. In a multi-step reaction, aka there's a step 1 and a step 2. Just like the weakest link is the strongest your team can be, one of those steps is going to be faster than the other by definition. The slowest step is referred to as the rate determining step. In other words, it's the one that determines the fastest your reaction can move. Sometimes the first step is the slow step. That's the one you want. Sometimes the second step is the slow step. That's the more complicated of the situations. We'll learn how to deal with both. Their analogy in this section is the toll plaza. Yeah.
So the rate determining step is the slowest step.
Correct. The rate determining step of a reaction is the one that is the slowest. Of however many there are. Okay, so let's talk about the first scenario, when the first step is the slow step. when the first step is the slow step, the rate law can be determined using the initial concentrations or the concentrations of the reactants in that particular reaction. In this particular case, CO was determined as not necessary because the rate doesn't depend on it. Now, whether that's because of an experimental determination or because CO is like a catalyst or it's something that gets canceled out when you add the two things together remains to be seen. But what we're telling you here is that the rate of the reaction, let's say this is the one step or whatever, is only going to be determined by NO2. Okay, so that's the first piece of information. Now, since CO is not involved, and this is the overall reaction, we're given the rate law is just related to NO2, the assumption is this must be happening in more than one step. And in fact, we're proposing a two-step mechanism. In this particular two-step mechanism, the first step is the slow step. The second proposed step is fast, so the second step does not determine the rate. Only your slowest step does. The rate law that we would get from our first step is NO2 squared, because there's two of them. In this particular case, carbon monoxide shows up in your second step. That's why it wasn't in the rate law. We can only go as fast as the slowest step. The NO3 you see on the right side appears in only the right and left side. When we add these together, don't we cancel out stuff on both sides? So NO3 is referred to as an intermediate. When it is produced in one step, then used in another, it is referred to as an intermediate. Okay, so that was our first, yes?
I just kind of got lost there. How do
Sure.
you determine which one is the rate determining step, which one's the slowest?
It would tell you slow and fast. Good question, yes.
You said, like if one is produced in one step and then used in the other, what's that called?
So if it is produced in the first step, used in the second step, it's referred to as an intermediate. Good question. You will be asked to identify intermediates. So in this particular example, do I have an intermediate?
C.
Yep. C is used in the second step after it is produced in the first step. Yes?
Step one, why would you see the lone NO?
It's in the final reaction. So what you're missing here, right, and I wish it was on the same slide, is this is the final reaction, right? So these are the things that are used and produced in the overall reaction. The two-step mechanism is this. So when you add those together, you should get NO2 plus CO makes NO plus CO2, right?
Yeah.
One of the NO2s technically cancels. Okay, so we talked about what an intermediate was, right? So produced, then used. The other thing we have to talk about is a catalyst. A catalyst is something present at the beginning that is also then used by the end. So it is not part of the overall reaction. This reaction up here on the board, this one, has a catalyst. Do you know what it is?
I don't know.
It's NO2. NO2 is not only one of the reactants, it's also a catalyst. It's present in the first reaction as a reactant, and then it's present as a product in the last reaction. So it is a catalyst. Catalysts are a little bit trickier to spot than intermediates, but they are both usually something I will ask you about when we talk about these types of problems. Yes?
So in the definition, you put cancel in the second product. I was thinking of
Yeah, so we could say present. Since it's present as a reactant and then a product, it gets canceled out. Just like this one.
Oh,
Right? Do you see what I'm saying? Like, when I say canceled, I mean since it's present here and here, they don't end up in the final reaction.
that wasn't the final reaction.
You can only spot intermediates and catalysts if you have multi-steps to look at. Yes.
So, intermediates and catalysts won't be present in the final.
Not present in final reaction. I'm just about to write that. Yes. Overall. Good questions. And we are going to spend a lot of time doing these problems. This is what we're going to work on tomorrow and Thursday. This is the last thing in chapter 14.
When's the quiz?
I mean, the plan was Friday, but probably Friday.
It was on the homework.
The plan was Friday, but yeah.
Right, so what'll end up happening inevitably is that we'll spend all day tomorrow and all day on Thursday working on reaction mechanisms
Yeah, we'll do it next
because we haven't done the actual manipulation of it yet. We're just talking about what they are first, and then we're going to learn how to actually do the math here. So we'll spend tomorrow and Thursday on reaction mechanisms. Friday will probably be your quiz.
Is that on the homework set?
But remember, Thursday's a double class, so. Huh?
Is that on the homework set?
Yeah, but
Yes, this is on the homework set, yes.
this week has been a lot.
This week is horrible.
Like, recap Monday.
I can't.
Recap Monday, quiz Tuesday.
I can't.
That's all I asked.
I know that's all you ask, but I also have been in chapter 14 for 2.5 weeks. I gotta move on, buddy. All right, here we go. Fast initial step.
Right?
Our fast initial step reaction has an overall reaction of this. The rate law is given. Seeing where this rate law comes from is kind of interesting in that it looks like it came from this original reaction, right? In this particular case, this reaction suggests a two-step mechanism. So a couple of things. One is, with our fast initial step reaction mechanisms, here's one rule. The first reaction is going to be fast and reversible. Okay, that's the first rule. It's going to be fast and reversible. Sorry, Carly. Let me know when you're done. The first reaction of a double step reaction or more that has a fast initial step, the first step will be fast, but it also must be reversible. Yes, ma'am?
So, it says that it suggests like a two-step mechanism. So, is it always going to suggest a two-step for first?
For these types of questions, I'll tell you right now, I wouldn't give you this and say, suggest two steps.
Okay.
I would always give you the steps.
Okay.
Okay, so I will always give you these things. And then I may ask you to tell me what the overall reaction is, and then I'll ask you to propose the mechanism. Does that make sense? Okay, and we're getting there. Are you good with me, Bina? Okay, so again, step one, reversible, fast. Those are the things you're looking for. Another thing we can still be looking for, intermediates and catalysts. Okay, so in this particular reaction, is there an intermediate? What is it? This guy, right? It's an intermediate Y, produced, then used, not in the final reaction mechanism. Okay, are there any catalysts? No. There are no catalysts. See, here's the thing. If it was a catalyst, it would be present here first, and then it would be canceled out in that last step. And this one doesn't have any. That's okay. They don't all have both. Okay. Since this is reversible, this has both a forward and a reverse reaction rate. They have forward and reverse rate constants. So you're going to start seeing little symbols like K1 and K negative 1. K1 implies forward reaction. K negative 1 implies backward reaction. Okay. this is stuff we are going to cover in depth tomorrow. For now, all I want to show you is that what we're moving towards is determining what the rate is of an overall reaction, given that it may have 2 or 3 total steps, using a couple of different things. One is predicting rate laws. Okay, so we can predict the rate law based on a couple of different factors. Our problem is if we used that slow second step to determine the rate law. So how do we write rate laws if we were just given a reaction? Does anybody remember from the very beginning? Well, we always write a rate law with rate equals K, right? Then we go concentration of the first reactant. If there was a 2 out front here, what would happen in our rate? It would be squared, right? So we would put this if there was a 2. All right, so that's the first one. What else is present in step 2? The concentration of NO. So this is the rate law, if you will, that we would predict for the second step. If the second step was the only step that we had to deal with, right? This was a while back, right? Like this was chapter 14, sections 1 and 2, predict the rate given just a reaction, okay? And we used just the general form of a rate law to determine it. Yes?
Wouldn't that be the rate for the overall reaction since it's a slow rate?
Correct, yeah. So this is the thing that we're saying they are predicting, okay? So that's where we're at so far. In the particular case of this second reaction, we're going to amend it just to say that this represents the second reaction by using a K2. So do you agree that this is the proposed rate law if the second step is the slowest one for this overall reaction? This is something that, in theory, you could get to yourself. If I said, hey, give me the rate law of just this reaction. Okay, the problem is, what did you just tell me about this? It's an intermediate. Intermediates do not stick around long enough for us to measure a concentration. So this is useless to me. I cannot have an intermediate in a rate law. It's a problem, okay? That is where these ones become a little trickier. So, there's a couple of different things that NLBR can do based on our initial 2 reactions. The first is it can react with NO to form NOBR. Okay, so this is one of the 2 things it can do. The second thing NOBR can do is decompose to become NO and BR2. Again, this all goes back to those 2 reactions that we proposed at the beginning. We said NOBR2 could react with NO to become this. We said NOBR2 could decompose, so remember it can go backwards in this first reaction, to become NO and BR2. Okay, so that's where we're at so far. Because of that, the reactants and the products of the first step are happening in equilibrium, which means the forward reaction is the exact same as the backward reaction rate. So how quickly the forward reaction happens is going to equal the reverse reaction. Do you agree? What do you think? If we said the reaction was reversible, does it make sense that how fast it goes this way is equal to how fast it goes this way? Yeah, you don't have any relation, you don't have any other information as to why it wouldn't. So that's a fair assumption. Because of that, and this is where we're getting into what we're going to talk about tomorrow, we can assume that the rate law of the forward reaction for that first step is equal to the rate law of the second reaction for that first step. From here, it's algebra. Yes?
Can you go back to the left side a little bit?
For which one? This one?
Yeah, this one. Okay, you're good. Thank you.
Okay. So again, we said forward rate equals backward rate. When we write a rate law, we write K times some stuff, right? Okay. So here all we've done is substitute in for that rate equation the forward and the reverse of that first irreversible reaction. Does this make sense? Do you understand where I got this stuff from?
Yeah.
Kind of sort of vaguely? That's all I need. Okay, from here it's algebra. These are all individual variables. In this, we solve for the intermediate. Why do we solve for the intermediate? Because we can't have it in our rate law. Remember, this is our proposed overall rate law for the whole reaction, right? We cannot have that intermediate. If we solve using this information for that intermediate, what do you think we're going to do with this? We're going to plug it in to this reaction. Plugging it in gives us something that looks a little bit like this.
So that's after both steps?
So this is after we take this, okay, and we plug it in to this reaction for this. Okay? Again, algebra. It's all good. Here's what we do. We multiply and divide by rate constants. Rate constants don't have units and are rate dependent, correct? They're reaction dependent. So can we just substitute a number for a number? Absolutely. What we say then, because these aren't actual numbers that are going to be measured, these are numbers we would calculate using experimental data. That's what you know about K so far. We say that K overall will equal NO squared times BR2. Again, this was the actual rate law from the very beginning. This is the thing they told us. They gave us this overall reaction and then said this. And we were like, okay. All you did was prove it. Okay. You survived the explanation. All right, so let's talk catalysts. Oh yeah, we're going to come back to it tomorrow.
Oh my god.
We already talked about catalysts. All they do is speed up a reaction. The way they speed up a reaction is by lowering activation energy. Remember that we said catalysts do not participate in the reaction. In other words, they are not used up. They're reformed by the end, if you will. So they speed up the reaction by lowering the activation energy specifically. They change the shape of the hill. They lower it. Make it maybe 2 instead. A little bit easier to deal with. They do change the mechanism of the overall reaction. Intermediates have no place in our rate laws. Catalysts either. Can we move on? Cool. All right, so there's a couple of different kinds of catalysts. More importantly, we care about ones that just kind of change the rate of our reactions. We're looking for ones that lower how long it takes or shorten the length of time it takes. We're also looking for ones that decrease the amount of energy required. So one thing they can do is they can just provide what we call a surface, right? So they can provide a place, a nice safe location for a reaction to occur. That's one thing that catalysts are really good at. The most famous kind of catalyst that you've seen before is, of course, the enzyme. And enzymes do exactly this. They provide a location for things to bind and break, or for things to break apart and then come together. We call them substrates for a reason. They are only there temporarily. They are not going to bind forever. They're specific shaped. It's like a lock and key method. Yes, ma'am? Sure. One of the ways, like we said, there's really 2 major ways that catalysts speed up a reaction. One is to just provide a safe space. The other is to provide a very quick space for things to happen, and that's what the enzymes do. They speed up a reaction by making it so that only the correct products and, only the correct reactants can actually fit into their substrates. That's why it's called the lock and key model. The substrate itself, so the thing that wants to break apart, has to be the specific shape that the enzyme has for it. Otherwise, it will not fit, and the enzyme will not let it use its space. This is what your body does all the time. I think that's it. That's my last one. Yeah, that's my last one. Y'all are really dramatic. Really dramatic. Like, we haven't been on chapter 14 for 2.5 weeks.
It's a long chapter.
It's intense. I understand it's a long chapter, and we have spent a long time on it. Kind of tired of the whining, I'm not going to lie. I didn't twist your arm to take the class. That's all I'm saying. Some of us are, and some of us aren't. What is it?
Not this class.
There's not a lot going on this week, so I'm trying to